So our next speaker is Devrim from İYTE. The title of the talk is Wigner Crystallization in Graphene Nanoribbons.
Thank you. Hi. So I'm going to change the subject a little. Okay, so there will be three main parts in my talk. First, in case you're not familiar with Wigner crystallization, I will briefly review the concept of Wigner crystallization in 2D and 1D electron gas. And then I'm going to focus on graphene systems, more specifically graphene zigzag edges. Okay, we'll first look at a single zigzag edge. Then after we understand that, we can move forward to the graphene nanoribbon, where you have two edges and they can be coupled to each other strongly. So we are going to look at that problem. And here's the motivation. Here I'm showing you a beautiful picture of a graphene nanoribbon fabricated experimentally last year. So it is actually experimentally very difficult to design such clean graphene nanostructures at this scale. This one was created using bottom-up approaches, so using chemical process. A lot of people try different methods. You have top-down approaches as well, but so far bottom-up approaches seems to give better results. So why these systems are interesting? As you can see, the edges are zigzag shaped, and it turns out if you solve the mean field, exact Hubbard Hamiltonian for this system, you get spin polarized edges. Okay, and the two edges are coupled anti-ferromagnetically. So this makes these systems very interesting for potential spintronic applications. In this talk, I will try to convince you that there is more to this story. Actually, this picture holds only when the system is charge neutral, and if you dope the system, so if you add electrons or remove electrons, there will be additional phenomena, more complex spin textures, structures, and Wigner crystallization at these edges. Now, I'm going to take a step back and look at a 2D electron gas. So this is not graphene. Just to explain the idea of Wigner crystallization. It is a strong interaction problem. So let's say you have a electronic gas, strongly, well, the Hamiltonian is given here. You have the kinetic energy and the interaction energy. And it is well known that if the density of the electrons is very high, this kinetic energy overcomes the Coulomb energy, and the system is weakly interacting, so it can be described as a Fermi liquid. On the other extreme limit, if the density is very low, it turns out the interaction term overcomes the kinetic term. Kinetic term can be neglected, and then the system behaves as a classical system. So the electrons become localized at their classical positions. So this is a Wigner crystal. So these two limits are well known, well understood. What is more interesting or more maybe complicated is how this transition happens, because for medium electronic densities, this Hamiltonian is not perturbative anymore. Okay, so you have to solve this exactly, solve the many-body problem exactly, most often numerically. You need to do that. And this was first done by Bilal Hoca in 1989 in this very famous paper. And this liquid to crystal phase transition, they found that it happens at an interaction strength defined here, around 30-35. So this interaction strength basically gives you the ratio between the interaction energy and kinetic energy. So what about experimental results? There are some well-known experimental result by Kravchenko in 1995. So they measured the resistivity at low temperatures. They noticed that as you increase or decrease the electronic density, the resistivity decreases. So, which is a signature of Wigner crystal, but it turns out this happens experimentally at 1015, RS 1015. Probably this is due to impurity effects, but it's not well understood. So later people start looking at alternative systems, quantum dots, zero-dimensional systems, and also one-dimensional systems. So I want to briefly talk about this 1D system. Again, these are semiconductor structures, okay, not graphene yet. The experimental setup was that they had two quantum wires. One wire was the reference wire, and the other one is the system wire, and they applied a magnetic field perpendicular to these two wires, creating a phase difference between the wires. And by applying a gate voltage and measuring the conductivity, they were able to trace the dispersion relation expected for a quantum wire. And what is interesting here, so B is proportional to K, the momentum. What is interesting here is that as you lower the electronic density by gating the system, at this point something strange happens. Here you have a zoom of this region. Okay, now you have a broad momentum distribution. So broad momentum distribution means localization in space. So this is a signature of Wigner crystallization. And it turns out this happens experimentally at 20 micrometer minus 1, which is close to our earlier theoretical numerical results of 15 micrometer minus 1. Okay, so this was for an electron gas. What about Wigner crystal in graphene? The electrons in graphene, as you all know, behave very differently than in semiconductors because of this linear dispersion. Okay, so you don't have a mass, and it turns out if you change the electronic density, you cannot force the system to go to a higher or lower Wigner crystal rate. So you cannot obtain two-dimensional Wigner crystallization in a graphene system. So people start looking at alternative ways. It is possible to obtain a Wigner crystal by applying an external magnetic field. You can open a mass term by confining the electrons in graphene. So this way you can have a Wigner localization. And also in 2012, it was proposed by Wang and Scarola that at the zigzag edges of graphene, it could be possible to have Wigner crystallization. So in this work, we are going to investigate in detail numerically what happens at these zigzag edges. So what is special with these zigzag edges? Here I'm showing the tight binding energy spectrum for different eigenstates. As you see, near the Fermi level, there is a huge degenerate band of 8 states. These are actually 8 states, which gives rise to these spin-polarized antiferromagnetic edges, as I told earlier. Now, what is important here is that whenever you have a degenerate state, that means that the relative kinetic energy of electrons sitting on these states is 0 or close to 0. So this system is dominated by interactions. It's non-perturbative. You have to include the interaction term to study this. And so for a charge-neutral system, this is what happens. And there is 1 electron per state. As we will see a bit later, if you change the number of electrons, if you change the filling factor, then it is possible to have a Wigner crystal. So we want to investigate at what critical density or filling factor this happens. And if we have a correlation between the coupling between the two edges, how this affects the Wigner crystallization. And as in the first step, so I'm going to consider a system with 1456 atoms that has 30 zigzag edges, and I'm going to focus on one edge to start with. So, which means I have 15 zigzag edges. Of course, now what we want to do is to solve the many-body Hamiltonian. So with more than 1,000 electrons, this is impossible to do. So what we do is we approach this problem in two steps. In first step, I'm going to remove all the electrons lying on the edge states. Okay. The remaining valence electrons can be regarded as weakly interacting. So we can solve the mean field Hamiltonian for this one. Once we do that, we have this new quasi-particle edge states, and now we can add electrons one by one. And each time we add an electron, we solve the configuration interaction many-body Hamiltonian and find the ground state. Okay. And from this ground state, we can investigate whether it is Wigner crystal or not. And to see that, we study the pair correlation function. Okay, so this is the pure state, many-body correlated state expectation value. Basically, it gives you the probability to find an electron at a position R if you have an electron at a position R prime. Okay, so here, for instance, this red cross shows the position where I fixed one electron, and the remaining is the distribution of all the other electrons. Okay. This one is for 14 electrons. Remember, I have 15 edge states, so I removed only one electron from this. Filling factor 14/15. And you see a uniform electronic distribution. There is no Wigner crystal here. Then if I do the same calculation for 8 electrons, then you start to see some oscillations. Actually, if you count the number of peaks here, you have 7 plus 1 fixed electron, 8 electron. So we are getting close to a Wigner crystal. And as you decrease the number of electrons, decrease the electronic density, this becomes much more clear. Okay, so here we have a Wigner crystal of 5 electrons and 3 electrons. So this is nice to see visually what happens, but to be more quantitative, more practical way of analyzing this is to take the Fourier transform along this direction. Okay. So if you do that, so I call this power spectrum. It's the Fourier transform along the zigzag edge as a function of the Fourier component k. Let's say for this blue curve is for 6 electrons, okay? And at k equals 6, I have this peak. So this peak gives you the strength of localization. For 11 electrons, the density is too high to give a peak. So I would expect a peak at 11 if there was a Wigner crystallization, but we see none. So there is no crystallization for 11 electrons here. And so we can plot these peak heights as a function of number of electrons. We get this curve. So above 10 electrons corresponding to a filling factor of 2/3, we see no Wigner crystallization, and below 2/3, we start to get Wigner crystallization. But the transition is not abrupt. So what happens to the magnetic properties? So as I said earlier, the edge becomes polarized if the system is charge neutral. Okay, here I'm showing the total spin as a function of number of electrons. Charge neutrality corresponds to this 15, okay, this one. Total spin is 7.5, so it is polarized. As I decrease the number of electrons, if the system was polarized, then it would follow this dash curve, but there's this depolarization effect. Some complicated spin structures. I will come back to this in the next slide, but let me tell you about what's going on. Here I'm showing the power spectrum, the Fourier transform, as a function of k for spin polarized and ground states. Okay, here the spin polarized s equals 4 and the ground state s equals 1 gives you the same power spectrum. Unlike for 10 electrons, there is a big difference. So the fact that the power spectrum is not sensitive to the spin is another indication of Wigner crystallization, which means that the electrons are sitting far apart from each other, well decoupled, so well localized. So let me come back to what's going on in this, how this spin depolarization happens. Here I'm plotting the spin-spin correlation defined here. So basically I have a fixed up spin at x equals 0, and I'm looking at the spin of the remaining electrons for different number of electrons. As the number of electrons decreases, you see that the nearest electron is getting far away. Okay, so because the density decreases, localization increases, and also the coupling between the nearest electrons switches sign. Initially it is anti-ferromagnetic, and then at the end it becomes ferromagnetic. So this affects the total spin of the system. Okay, so this was for one isolated edge. Now let's look at the nanoribbon, where we have two edges that can be coupled. Here again I'm showing the total spin, ground state total spin, as a function of number of electrons. 0 means here is the charge neutrality. Okay, and we looked at different lengths and widths and boundary conditions. When the system charge is charge neutral, you always get anti-ferromagnetic edges. This never changes. This has to be like that because there's a Leibniz theorem that says that solution to the Hubbard system must give you total spin 0. But away from charge neutrality, similar to what I explained earlier, there's this complex spin phenomena, and this total spin is very sensitive to the dimensions of your system. Now, from now, I'm going to focus on spin polarized electrons. I'm going to ignore the spin effects. Okay. So here again, I'm showing the pair correlation function. Now for a ribbon with width 12 Armstrong. Why 12 Armstrong? Because this picture that I showed earlier, experimental one, has a width of 12 Armstrong. The fixed electron is here. I have 2 electrons in this system. So you see that the remaining electron is completely delocalized. There is no Wigner crystal here. We repeated this calculation for other parameters, longer ribbon, same thing, the electron is fixed here, and the remaining other electron is completely delocalized. There is no Wigner crystal. Now, why this happens is that the width is very small. So the 8 states are strongly coupled to each other. There is a hybridization, the degeneracy is lifted, and the electrons gain kinetic energy, and then it competes with the interaction energy, and in this case, the kinetic energy wins over the interaction energy. However, if we increase the width to 28, okay, again, the same calculations, electron fixed here, and the second electron is localized at the opposite edge. Okay. Same thing for the longer ribbon. This is for 2 electrons. If we have 3 electrons, it seems that, well, we have fixed electron here, one electron localized here, and in the opposite edge, it seems there is no localization. You may think, well, you increase the electronic density, so you lost the Wigner crystallization. Let's increase the density more to 4 electrons, but then again, you recover the Wigner crystallization. one fixed electron here, one here, and one here. There's periodic boundary conditions. So what happens in 4 and 3? This is due to the fact that there's an even-odd effect. So you have 3 electrons, you have to share between two edges. There's frustration, which is why you seem to not get Wigner crystallization. Okay. So we repeated these calculations for different widths, and here I'm showing the power spectrum peak. Okay, and it turns out that around 18 Armstrong, below 18 Armstrong, you don't get Wigner crystallization, and so if you are trying to design some spintronic device and you want to eliminate Wigner crystallization, then it has to be thinner than 18 Armstrong, depending on your application. We also looked at the effect of electric field. Okay, so in this, we apply an electric field in this direction, creating a potential difference between the two edges. So the edge states, now there's a lifting, the generously lifted between the edge states. Again, if you have a low electric field, you have nice localization, but as you lift the degeneracy, the coupling between the edge states is suppressed. So in the opposite edge, there is no more localization, but some charge oscillation, delocalized charge oscillations. So this gives you a possibility to control the localization by applying an external electric field. And okay, finally, we also looked at hole localization. Okay, what I mean by hole is that so if I have 2 holes, this means I have fully occupied, doubly occupied edge states, but I remove 2 electrons. And again, we can observe Wigner localization of holes. Okay, but it turns out that the hole localization is weaker than electron localization. For 3 holes, we start losing the localization, and for 4 holes, we don't see localization on the opposite edges. Okay, so to conclude, we find that there is a liquid crystal transition near filling factor of 2/3 at the graphene zigzag edges. We observe a ferromagnetic antiferromagnetic transition between the neighbor electrons during this crystallization process. We find that the crystallization is suppressed for ribbons thinner than 18 Armstrong. So most importantly, we show the importance of Wigner crystallization for the design of carbon-based spintronic devices. Thank you.
Does the two-step formulation taking into account the crystallization effect on the original mean field of the valence electrons? Or is this
in valence electrons, we assume that there is no crystallization, right. So we just...
And then you build this edge state on top of that.
On top of the mean field solutions, yes.
So my question is, does that, do you need to worry about this new density disturbing the original mean field?
Yes, you should worry about. Well, we did convergence tests, so if I go back, it's not clear where you put this limit, where you consider which states are valence, which states are edge states. It's not very clear. So we did a convergence test. We changed the limits of the valence states and we saw that the results were converged. It does not change after at some energy level. It doesn't change anymore. So.
Kinetic energy per electron is constant for the edge state. Kinetic energy per electron. So kinetic energy per electron is constant for the edge states.
Yes,
So,
if you have a nicely degenerate.
So
state.
intuitively, increasing the density should induce Wigner localization, right? Because
Increasing the density.
yes, because
Usually it suppresses the.
But I mean, Coulomb energy is inversely proportional to the mean distance, right? Kinetic energy is constant per electron. So intuitively,
You mean for graphene, or
for
you're talking about
for
the
the edge
electron
states,
gas?
for the edge states, I mean, right? I mean, kinetic energy is constant.
Yeah, it is a bit more. So I talked about hole localization. If you keep increasing number of electrons, then the hole starts to get localized. There is still localization if you increase the number of electrons. But near the charge neutrality, there is no Wigner crystallization. Above or below,
Okay.
you will have
Okay.
Wigner crystallization.
Okay. Thank you. Okay. So let's thank the speaker again.